Hi everyone, welcome to this continued video series on essential statistics, a primer for data science and machine learning project. In the previous video, we talked about the context and the overview and why knowing or knowledge about data science is dependent on statistics and some amount of mathematics. We also talked about the table, the tabular structure, and also the feature types. In this video, we'll look at the first topic in statistics about population and samples. So let's get started. The concept of population and samples is very important in data science, statistical projects, and machine learning as well. So some of the areas where we use the population and samples are the defining the target group, conducting inferential statistics, conducting hypothesis testing, model evaluation. So in machine learning, when we evaluate multiple models, that's where the concept of sampling becomes very, very important. So let's get started. The first is the definition of population. And along the way, I'll be also showing, the Python code demos for each of the mini topics. So let's define the population, which is basically a definition for entire population. That means when you're talking about, let's say, any group, so that would be all the members in the group. If you're talking about, let's say, cars, then all the cars in that region or the cars made by the company, and so on and so forth. Let me give you a few more examples. So examples, smartphone users, that means all the users, registered voters, and so on and so forth. So that's the definition of population. Is it possible to get the data set which represents every member? Possibly not. So this is where sample comes. So sample is a subset of the population, and that is used quite frequently in most of these statistical projects, including data science and machine learning. Some of the examples of samples would be, let's say, randomly selected survey respondents, quality control testing. So in when the products are in production, then we look at a particular batch of samples, and examining that sample helps us, also infer about the total population or total production, maybe in terms of defects or in terms of, some quality metric. So let's take another example. Suppose you are interested in studying political preferences of all the voters in a region or a state or a country. Then entire set of eligible voters is your population. Consider that maybe it's millions of individuals, and it's really not possible to conduct a survey with millions of individuals. So instead, what we do a sampling. And the reason we do sampling is it is impractical to survey every eligible voter in the country due to time and resource constraint. So instead of entire population, we just choose 100 or maybe thousands of voters and do the survey. Now in this video, we'll talk about how do we select the subset or how do we select the sample. There are few strategies that we can keep those in consideration when we select those samples. So this 1000 voters is the sample. So some of the sampling techniques that we use, the basic one is called simple random sampling, where every individual or every member or every data point in the data set has an equal chance of being picked up as a sample instance. So it's commonly implemented method that we use to select a data point as a sample is random number generator. We'll look at the Python example and we'll see how do we use random number generators to pick the sample. Another technique is stratified random sampling. This is useful when the population is divided into homogeneous subgroups, and these groups are called strata. And of course, the grouping is based on some attribute. It could be something to do with age or gender or region or the language spoken or the income level. So it could be any of these dimensions. Then we draw the sample randomly from each of these strata. This is called stratified random sampling. So this helps ensure every group is represented. Let's say we have 10 subgroups in the data set. With simple random sampling, some group may be left out. With stratified random sampling, since we are considering all these strata, so all the subgroups will be represented in the sample. Simple random sampling, the technique is quite easy. It's a basic method where every individual has equal chance, and it doesn't take any predefined rule or a structure of the population into the consideration. So the only criteria that we use here is each individual has the same probability of being picked up. So when to use this simple random sampling in machine learning or data science? When we want to do preliminary analysis of the data. Suppose we are dealing with a large data set and you want to do some, early assessment of the data. So we might prefer simple random sampling. Model evaluation, when we have a machine learning model and the prediction results, we might want to do a simple random sampling from the prediction results to validate, or we use the validation set and we pick the data randomly from the validation set to test the model. Other use cases is suppose you want to ensure fairness in the representing the population, then simple random sampling method is useful because there is no bias here. And homogeneous population, that means if you know the data set is homogeneous and there is no variation in terms of distinct population, we can use this method. So for homogeneous population, the simple random sampling is very useful. Some of the considerations that we have to keep in mind, this simple random sampling is straightforward, but there is a risk here that the sample may not fully represent the population because this is based on random picking of the data from the data set. Especially if the sample size is small or the population has a significant variation in the original definitions. So in such cases, we have to depend on some other techniques. I'm going to show you a little Python demo using a simple random sampling. So this is a simple, code where I have some data set here, and I'll just pick randomly, the sample of 3, and then we can use the NumPy or random package and use this sample and then mention your data set and provide the sample size. Is going to pick up any 3 here because any of these, each of these individuals here have equal probability of selection. So this is simple random sampling. So that was a quick demo on simple random sampling. Let's move on. So the next type of sampling method is stratified random sampling. So stratified means the layer or the group or subgroups of data. So this is to ensure the representative sample or the sample that you draw is from a population, dividing the data into distinct subgroups. And then we randomly sample from each of these subgroups. And the method helps essentially in capturing the variability present in each of the subgroup. Let's say you have 10 subgroups in the data set, and the stratified will look at all the 10 subgroups, and from each of the subgroup is going to randomly pick the samples. So this is the meaning of capturing the variability within each of the subgroup, because we are addressing each of the subgroup. This is very useful when we deal with imbalanced data set. That means you have certain data set where you have class A being majority, class B being minority or very small, and you want to make sure these samples are picked up from both the classes. Then stratified random sampling is the method that we use. So some examples here, let's say in the healthcare, suppose you are conducting a clinical trial to test a new drug, and you want to ensure the sample includes the proportional representation of different age groups or gender or race or ethnicities and all. So these are all dimensions. So based on the dimensions, you could have subgroups. So stratified random sampling can be used to select participants from each of the dimensions. That is the meaning of stratified random sampling. Let's look at one more example, credit scoring. Here you may have a data set with customers having different income levels or different credit histories. Now, in order to build a well-defined or generalized predictive model, you have a goal to build a system which can predict the credit worthiness. Then in that case, we need to do a stratified random sampling, ensure the data is coming from each of the income level or each of the credit profiles. So this will ensure a fairness or a better representation of data. So sampling techniques used in data science. Now I'm going to use some new techniques, but before I go, I'll show you a Python code for stratified random sampling. So this is the code here. Let's say I have the data category A, B, and C, and these are the values. So our strata, there are three stratas, E, A, B, C. We can define a little function to make sure you're picking the data from each of these strata or the group. And let's say you have requirement of selecting samples from each of the strata and two samples from each of the strata. So using this function, you can ensure category A there are two samples, and B two samples, and C two. So in machine learning and data science, you're not going to be writing this function. This function I just wrote it to demonstrate, but Python packages for machine learning will do it for you. So you just have to pick the right library and it will automatically do the stratified random sampling for you. Okay, let's talk about some more techniques for sampling. Uh, let's talk about systematic sampling. So this involves selecting by some kind of a heuristic or something like a rule. For example, you may select every nth data point from the data set. For example, you have a list of customers and you want to make sure that you're taking or picking every 10th customer from the sample. Obviously, this will require some kind of pattern in the data. It could be sorted based on some criteria, and then you pick every 10th customer. So this is called systematic sampling. One more technique is called cluster sampling. So let's talk about it. Here the population is divided into clusters. For example, the geographical regions, and for each region you could have schools or hospitals. Then what we do, we pick the random regions or random number of regions. Let's say I have 20 regions and each region has schools. Then the 20 regions, we will pick the random number of regions from those 20, and then after that we will select all the schools or hospitals from the selected regions or clusters. So this is called cluster sampling. One more method is called probability proportional to size, or rather weighting based on some weights. So this is useful when the elements or the data points have varying probabilities of being selected based on some attribute. It could be frequency or importance or size. It could be anything. So the elements of larger values will have more probability of being selected. So let's talk about these three techniques one by one. Systematic sampling is to select the sample from the larger data set using some kind of a systematic method or heuristics or in a structured manner. For example, let's say you start with a random starting point, and then after that, every nth data point you want to include in your sample. So this is more efficient than simple random sampling. Yeah, so this is more efficient than simple random sampling that we saw in the beginning. So how systematic sampling works, just a little bit of elaboration. So randomly select the starting point within the data set, and then this can be done by some random number generator. I mean, let's say you have n number of samples, n number of data points, just select, randomly any starting point, and then from there on, you decide the sampling interval based on a configurable parameter to determine the sampling interval, which is the number of data points between each of the selection. For example, if you have 1000 data points and you want to sample 100 samples out of it, so your interval would be 10, 1000 divided by 100. So after that, you're going to select every 10th element from the data set. So let's say, so this is another illustration of systematic sampling. Randomly sampling, let's say the starting is, let's say we are interested in picking 7th customer. Determine the sampling interval, which is, let's say, 1000 total customers divided by the sampling size of 100. So that's the interval. So we're going to select the 10th customer. That essentially means the customer number 7, 17, 27, 37 until you reach 100 customers. So this is systematic sampling. So when to use systematic sampling in our data science and machine learning? Obviously, this is more efficient because you're going to save time and resources compared to more vanilla, simple random sampling. It's good for large data sets, is well suited for large data set. And time series data, where the data is ordered by time, systematic sampling is very, very efficient and useful there. And as such, it maintains the little bit of randomness in the data because starting point is randomly picked. Slight note here, systematic sampling may introduce some bias if there is a pattern or periodicity in the data. Means there is some kind of an order, and based on the, since we are picking the data after nth sample, so that might introduce some bias in the samples being selected. To mitigate this, we have to make sure the selection of the starting point and the interval has to be given a good thought. Let's take a look at the Python implementation of systematic sampling. So here is a simple example. Let's say I'm generating some random data and we are making a little bit of a mechanical order, like sort, and then we perform the systematic sampling. So first we define this step. Let's say after every 8 element will pick up. So we can use numpy arrange method, and so let's say we're going to start with element number 0. This is configurable. So starting with this, then you pick up the element number 8, 16, 24, and so on and so forth. Now you can design it slightly more in a complex way to make sure the starting point is different and the intervals are also configurable. So quite a simple method, and now after you got the indexes, you can get the data as well from the list. So this works very well with time series data, pretty much the same method. In the time series data, you don't have to sort it because data is already sorted by time. If it is not sorted by time, then you have to sort it by time in any order of your preference, like ascending or descending. So that was a quick demo on systematic random sampling. Let's talk about one more method called cluster sampling. And this involves dividing the whole data set into clusters or groups, then selecting a subset of these clusters randomly. So for example, let's say we have cluster 1, 2, 3, and then from this we select cluster number 2. And then after that, in this 2, we're going to take all the samples from here. So that's how the cluster sampling actually works. The advantage of cluster sampling is, again, you're bringing some variability or randomness by choosing the clusters randomly. Once you choose the clusters, then within the cluster, all the data points you're going to collect and put it into the samples. So let's see some examples of cluster sampling. Let's say in the healthcare field, hospital patient records, you may want to group the hospital by location or by size. And instead of collecting, data from all patients, what we can do, we randomly select a subset of hospitals. Then collect the data from all patients within the selected hospitals. And likewise, let's say images, and you have, you might have organized the images into categories, and then within those categories, randomly pick some categories, and then after that, chosen categories, we will pick all the samples from those categories. So when to use cluster sampling? When you have large population, is very efficient. And of course, resource is a problem. Then you look at cluster sampling, especially for spatial data, geographic data, location, longitude, latitude, region, district, state. This makes more sense to use cluster sampling. Natural grouping, where things are naturally grouped, cluster sampling can be a very, very effective tool. But there are some disadvantages of cluster sampling as well, especially when you have heterogeneous data. If there is substantial variability within the cluster itself, then it can lead to bias estimate because you are picking all the samples from that cluster. So, for example, if you're studying income levels of different cities, some cities may have wide income range and you are picking those samples in your study while ignoring the other city. If the other city is not picked up as a cluster, then you're going to be missing out on those. So loss of data is also one factor that we have to consider. Cluster size variation is another factor. So unequal cluster can lead to again data imbalances. So we have to make sure the cluster sizes are equal. Cluster sampling assumption assumes that the clusters are independent. Here we have 20 clusters and we make an assumption that these clusters have nothing to do with each other, so they are independent. Now, if that is not so, there is dependency, then the sampling would be somewhat erroneous, and that will reduce the generalizability of the model. Let's take a look at the Python example again, pretty straightforward. Let me show you an example there. So here is the cluster sampling example. Number of schools is 5 and students per school. So I'm generating some data here. And then hypothetical data set with the scores. So like, some students scores here. Okay. Now I'm going to be, so we'll repeat this so that we have a, data set, that's a dummy data set. Then you group this. So it's like school one, this is the data, school two, this is data, school three, school four, school five. Now let's say we are interested in randomly picking two schools from here. So random choice, pick the two schools out of five, and those are selected schools. These are my selected schools. We are not selecting the other schools here. So that was the disadvantage that we spoke about. Now after this, you can just sample for those selected school. For each of the selected school, get the data, and that's your sample now. So this is the sample based on the selected school, school number 4 and school number 2. I hope this example was pretty straightforward, and this is called cluster sampling. So we talked about cluster sampling. Let's talk about one more method. Is called reservoir sampling. It's pretty easy. This is very useful in situations when we are dealing with streaming data set. That means the data is coming live and then you have to sample. So in this case, what we do is we will randomly, sample the fixed size of, potentially very large or streaming data set. Now, in streaming dataset, it will be very hard to keep all the samples there in the dataset. It's particularly useful in the continuous stream of data, for example, in machine learning models where the data is streaming, for example, IoTs and sensors and devices and so on and so forth. Let's see how reservoir sampling actually works. So we're going to initialize the reservoir, start with the empty reservoir or simply like a data set or like an array or a dictionary of desired sample size. So this desired sample size is a configurable parameter. So as you encounter each data point, you will assign it to the reservoir. Now, first, what we need to do is initially the first data point that came in your stream, we will pick those and put in the reservoir, where K is the desired sample size, and let's say that is 1000. And after that, we will utilize a random replacement. That means after the first K data points are placed in the reservoir, your reservoir is full. Then for each subsequent data point, we will randomly remove this one sample from the reservoir and replace it with the new one. The idea is very simple. We apply the probability of replacement is equal for all the samples in the reservoir, and that's K divided by all the total processed data point. Now you notice here what is happening is K is, let's say, 1000, and total data point will keep on increasing, let's say 2000, and after that this would be 1000 over 3000, and so on and so forth. Look at the denominator keeps changing because of the streaming nature. So the probability of the points that is there in the reservoir will keep changing, and then based on the probability is going to pick the sample to be replaced with the new data entry. So when to use reservoir sampling? It is useful when you are dealing with a data stream or continuous flow of data, and you need to maintain a fixed size of sample or representative sample without storing the entire stream of data. Especially useful when you're dealing with large data set which cannot fit into a memory. And uniform random sampling. So if you require uniform random samples from the large data set, reservoir sampling actually ensures each data point has equal probability of being included in the sample. So this is what it is here. The formula ensures that every sample in the reservoir is equally likely to be picked out and replaced with a new entry. So this is useful when you have homogeneous data and a large stream of data. So there are some downsides or some key note to consider in reservoir sampling. It doesn't guarantee the sample is perfectly representative because it's randomly picking the sample from the reservoir. Especially if the data distribution changes, then there is no guarantee that you have a fair representation. So it provides a good approximation and it's a pretty useful tool, especially when we are talking about streaming data set. Let's talk about, or let's see a Python demo. Okay, so let's take a look at the Python implementation of reservoir sampling. This is just an illustration here. So I'm generating a stream of 100 numbers starting from 1 to 101. So that's my range. So in the reservoir sampling, to sample k items here. So the parameter stream can be anything like a list or dictionary or any generator. Parameter k is the size of the reservoir or size of items to sample from the stream. So this is my reservoir to initially empty, and the size of the reservoir we want to maintain is 10. So we want to maintain the size of reservoir as 10. Let me walk you through exactly what is happening here. In this for loop, we will look at this stream. So I'm just simulating this stream here. in a loop. So for the first 10 records, they will go into the reservoir. Okay, and after that, when the reservoir is full, then this part will not be executed. So we will come to the else part. In the else part, what is happening is we're going to do a random integer being generated. So j equals to, between 0, and let's say in the stream we are processing record number 31. So it's going to be randomly generating some integer, maybe 17, for example. So then what we do here is we check if j is so j is 17, is it less than k, which is 10? No, right? So we don't do anything. But instead of 17, if it is 7, then 7 is less than 10, then we replace. So we go to the reservoir, and in place of 7, we put the new item that has come in the stream. So that way you can maintain the reservoir size to 10. And you notice this is just one way of implementing the probability. You can design the probability of selecting in different ways as well. So what it means is as the streaming size increases, let's say j is random integer from 0 to, let's say, 10,000. That means the number between 0 and 10 being picked up is smaller and smaller as the range goes bigger and bigger. So that means you will replace the reservoir only when the randomly generated number is between 0 and 10, and then you replace the reservoir. So this is one smart and intelligent way of handling streaming data. At the same time, you can ensure a good representation for data which is really growing because of the streaming nature. I hope you appreciated the point. And one more time, the reservoir sampling. This was just illustration. You can implement in different ways as well. So that was a quick Python illustration on reservoir sampling. One more technique which is commonly used in machine learning, and this is called bootstrapping. This is useful when you want to generate additional samples from the existing data set, or you want to have some variation of the data set that you have, and you want to have more variation of the same data set for your machine learning. So this also involves repeatedly drawing random samples with replacement from the dataset or original dataset. So when to use bootstrapping, especially when you have a small dataset and you want to have variation of the dataset. I'm not going to cover bootstrapping here. I will cover more when we discuss machine learning, especially boosting based or ensemble based models. We will talk about bootstrapping. So just to summarize the use cases of sampling, I have listed a few of them. You could apply sampling techniques in almost any statistical or data analysis. The sampling and inference projects, let's say you want to establish some conclusion based on some samples, or you can want to conduct some hypothesis testing. Again, the usage of samples is very, very useful. Or you want to do some market research, and based on some samples, you can establish some hypothesis on the bigger population So this is all that I wanted to cover in terms of sampling techniques used in data science and machine learning. The next topic we will cover would be centrality of the data. And yeah, just a second. Yeah, the next topic I'll cover is central measures, mean, median, mode, and again we will discuss their relevance in data analysis, especially machine learning and data science. Have a great day, guys. We'll see you in the next lecture.